Welcome back to PChem 2. I hope everybody's doing well. This will be our first video and my first attempt at a video in quite a while. We're going to start into Chapter 9, which deals with the hydrogen atom. So now we're really getting into the quantum mechanics of chemistry. We're going to start talking about the energies associated with electrons, how we know they are what they are. This is really going to be the beginnings of looking at how we got to electron configurations in Gen Chem, how those things were known to exist. And so we're going to begin with thinking about the Schrödinger equation. We know that it's the Hamiltonian acting on a wave function, giving us the energy times the wave function. And so what's the Hamiltonian going to look like for the hydrogen atom? Well, it's very similar to what we've seen before. It's negative h bar squared over 2m times the second derivative, second partial would be a better way to say that, with respect to x, plus with respect to y, plus with respect to z, of the wave function, plus a potential energy function times the wave function. Now, the hydrogen atom is not rectangular like particle in a box problem was. And so we're going to be looking at a spherical item, and so it makes a lot more sense for us to use spherical polar coordinates for this version of the Hamiltonian. And so what we've done in this area, you don't have to memorize this part. This will be given to you on tests if it's necessary. But that is a mathematical conversion of this sum of second partial operators to spherical polar coordinates. It's a derivation we could do. It's one you may have done if you took Calc 3 or Calc 4, whichever one that they do those in. Now the other thing that we need to think about is what this potential energy operator looks like. And so on the next slide we'll show that. The potential energy associated with electronic attraction between a proton and an electron is E squared, where E in this case is the charge on an electron, not the inverse natural log function, over 4 times pi times permittivity of free space. We talked about this during the Bohr derivation. And the radius, the distance between the electron and the proton. And we have a negative sign here because it's an attraction energy. If it were a repulsion energy, like 2 electrons would feel for one another, then we would have a positive sign there. So we put that into the Hamiltonian, and now we have our full Schrödinger equation. Now look what we've done here. We've distributed the wave function to the several terms that are in the Hamiltonian, rather than keeping it outside. And so we need to find, in order to solve the Schrödinger equation, wave functions that fit this particular Hamiltonian. Now, in order to do this, what we're hoping is that we'll be able to use separation of variables like we have in the past and write a wave function that can be separated into 3 separate functions, one of which depends on radius, one depends on theta, and one depends on phi. And the other thing to notice is that the angular portion, the non-radial portion of this, looks very, very similar to what we saw for 3D rotation in Chapter 7. And so the angular portions of the wave function, when we are able to do separation of variables, the theta and phi portions of the wave function are going to be the same as, or very similar to, what we saw of the spherical harmonics in Chapter 7. So if we substitute that in there, now this is going to start to look more and more complicated for a second or two, and then it'll get a little bit easier. If we substitute that in there, we see a full-fledged Schrödinger equation that looks like this. So functions for r, theta, and phi have been substituted in for psi, And in the cases of where there is a derivative being taken, only the function that relates to that variable for which the derivative is being taken remains in that derivative. The others act like constants and are pulled out in front. And so we've converted our partials to full derivatives since we were able to do that. And so now we have a full Schrodinger equation with those functions. If we distribute the negative h bar squared over 2me, where me is the mass of an electron, and recognize that the operation on the angular portion is the same as the L squared operator from chapter 7, then we get a slightly simpler looking version of the Schrodinger equation that we can start to work with and start to play with. Now, on the next slide, I'm going to show you a mathematical justification for this, for converting all of this angular portion to the L squared operator. And then on the following slide, we'll go back to working with this equation as it's written. So let's take a look at that. By the way, as you're working through these videos, please feel free, because I know I'm going faster than I normally would in class, and I know that I go fast in class to begin with. Please use the fact that this is a video lecture instead of me in person to your advantage. Pause the video, rewind it, and listen again when you need to. Pause it to get things copied down. Listen to the parts that you need to over and over again. So this will probably be a 15-minute video when I finish, and the rest of the videos will probably be between 10 and 15 minutes each. But it might take you an hour to watch them well, and to use them in the best way that you can to generate notes and thoughts and concept maps that will mean the most that they possibly can to you. But like I said, the mathematical justification for what we've done here is energy with respect to L we had defined as the Hamiltonian related to L, and the eigenvalues for that were just h bar squared over 2I times L plus 1, where L is a quantum number. And so the L squared operator is h bar squared times L plus 1, which means L times L plus 1 is just L squared over h bar squared. And the Hamiltonian portion of the operator that deals with L then is just the L squared operator eigenvalues over 2I. So take a look at this slide, substitute it back into what we've done so far, and try to think that through. I wish you were here so that we could go over any questions that you may have. I hope that if you do have questions on any of these parts, that we'll be able to answer them or deal with them over email. What may happen is one of you may ask a question via email, and I may respond to that by copying the entire class on my answer. I'll try to remove identifying information from who asked the question, just for privacy's sake. But that way the whole class is seeing the questions and the answers that come up via email. So please, as often as you can, keep checking your email throughout the rest of this course. All right, so back to our Schrodinger equation. If we operate with that L squared operator and put that L squared eigenvalue in, then we can divide both sides by the angular portion of the wave function, and that all drops out. So we end up now with a very simplified looking version of the Schrodinger equation, where the wave function that's left only is dependent on the R portion of the wave function. And we can rearrange this a little bit, and I'll leave it to you guys to leave some space between these two lines in your notes, and do the algebra yourselves. Make sure you can get from one to the next on your own. We have a little bit easier version of this item to work with. So energy times the R portion of the wave function is negative h of r squared over 2mr squared ddr of r squared times d, the wave function dr, plus this item here, which we're going to call the effective potential. So it contains the potential energy and an L quantum number related term that we're going to call the centripetal potential. So we've got two new terms for our definitions. This one is the centripetal potential. This one is the effective potential. I'm sorry, this one is the centripetal potential. This one is the Coulomb potential. And together they make up the effective potential. Let me see. Something to point out, the centripetal potential goes as, or is directly proportional to, 1 over r squared, whereas the Coulomb potential goes as, or is directly proportional to, 1 over r. So like I said, we've discovered the form of the angular portion of these wave functions back when we were doing rotational spectroscopy. They're the same spherical harmonics that we've looked at before, but we don't have functions yet for r. We can do this mathematically, but it's somewhat tedious. I'm not going to show it all right here. But the boundary condition for r is the boundary condition r goes to 0 as the wave function r, the value of it goes to 0 as the radius goes to infinity, introduces quantization into the problem. And so we're going to have an n quantum number here, where n can be 1, 2, 3, 4, etc. The radial functions then are products of an exponential function and a polynomial of the dimensionless variable r over a0. And we'll talk about what a0 means a little bit later. But the first several radial functions can be found in Chapter 9 in the book. You can look those over on your own. Remember, I've placed a PDF of the textbook in the D2L folders, so that if you didn't bring your textbook home with you, or you don't have a copy to look at right now, you'll be able to look at those on your computer. And you can look at those, don't memorize them, but we may work with those, particularly when we get to the example portion of this. We'll look at those to determine nodes, like we were doing with the rotational functions. So the wave function then depends on the quantum numbers n, m sub l, and l. The m sub l and l portions come in from the angular portion, but the energy only depends on n with the hydrogen atom. Again, we could show this mathematically using those radial functions from the textbook, but the energy works out to be negative me squared, where me is just the mass of an electron, times e to the fourth over 8 permittivity free space squared, h squared, n squared, and that can be simplified a little bit to get us down to this, which means that the energy is just a certain number of joules over n squared. The energy goes as n squared. A0 is referred to as the Bohr radius, and it's a collection of constants that have a distance units, meters units, or angstroms in this case. But it works out to be about half an angstrom. And it removes some of these constants from the energy term. That's about all the time we have right now. We're going to pick up with the next slide, which will talk about degeneracy on the next video.